Imagine a planet frozen to -50 degrees, where a kilometer-thick ice layer seals every ocean from pole to equator. The air is bone dry, snow barely falls, and the entire globe seems suspended in a quiet, terrifying, frozen death. This is not a distant alien world. This was Earth 700 million years ago, during a phenomenon called Snowball Earth. Paradoxically, these devastating planetary freezings were not death sentences, but the ultimate evolutionary engine for complex life. Today, we uncover the complete saga, from ancient global glaciations to the recent ice sheets that formed human civilization. Consider one astonishing number that reframes planetary history: 80% the time Earth spent in glacial cold. Over the past 2.5 million years, Earth was mostly a harsh, freezing, and intensely hostile world. The warm interglacial climate we enjoy, where every human empire rose and fell, is actually a brief, rare anomaly. Human civilization was born in a temporary 12,000-year pause, as retreat of ice sheets allowed sea levels to rise. To understand why our planet freezes, we must abandon the illusion that warmth is Earth's natural default state. Long before the Pleistocene ice ages, Earth endured a freezing event so absolute it shattered the boundaries of life. Known as the Cryogenian period, from the Greek words for cold and birth, this era generated intense biological leaps. Geologists proved global ice cover using paleomagnetism, analyzing how magnetic minerals aligned when ancient rocks crystallized. Magnetic alignment horizontal to the ground indicates rocks formed precisely at the warm equator 700 million years ago. Yet Cryogenian glacial tillites and dropstones are embedded directly within these equatorial rock layers across multiple continents. The geological evidence is undeniable. Glaciers were actively carving land in regions that should have experienced tropical heat. To force glaciers to the equator, ice must have enveloped the entire planet, freezing every ocean without exception. Another proof lies in the marine carbon isotope record, which tracks biological productivity across the ancient seas. When photosynthesis collapsed beneath frozen seas, carbon isotope ratios plummeted into massive negative swings worldwide. These isotopic flatlines reveal a planet where marine life nearly ceased to exist before rebounding in explosive pulses. The Cryogenian saw two monster glaciations, the Sturtian lasting 50 million years, followed by the Marinoan. Together, they represent nearly 75 million years of continuous planetary ice, dwarfing any recent ice age. How does an entire planet freeze over? And more importantly, how does it ever escape a frozen death sentence? The trigger was a catastrophic runaway process, driven by the powerful ice albedo feedback loop. White ice reflects solar radiation back into space, cooling the surface further and driving ice expansion to the tropics. 700 million years ago, the breakup of supercontinent Rodinia placed most landmasses near the equator, when ice covered these tropical continents. Their high reflectivity pushed the cooling feedback past the point of no return. Additionally, the sun was roughly 6% fainter, providing significantly less thermal energy to resist the freeze. Once initiated, the Snowball Earth state became exceptionally stable, shutting down evaporation and global water cycles. Without liquid rain to scrub atmospheric carbon, a secret escape mechanism began accumulating deep beneath the ice. Volcanoes do not stop erupting simply because the surface above them is sealed under a mountain of ice. Driven by internal heat, active volcanic vents poured continuous carbon dioxide into the atmosphere for millions of years. Without open liquid oceans or rainfall to reabsorb carbon, greenhouse gases built up to extreme toxic levels. Carbon dioxide concentrations soared hundreds of times higher than modern levels, trapping immense thermal energy. Eventually, global greenhouse warmth surpassed the reflectivity of equatorial ice, triggering a sudden, violent meltdown. The ice albedo feedback ran violently in reverse, melting global ice sheets in a matter of millennia. The immediate aftermath was not gentle warmth, but an intense, hypervolatile, super greenhouse climate. Equatorial temperatures surged to 50 degrees Celsius as torrential acid rain battered the freshly exposed land. Enormous rivers poured dissolved minerals into oceans that had been isolated from air for tens of millions of years. Yet, amidst this apocalyptic cycle of freezing and boiling, simple life found a way to survive. How did fragile biological organisms endure when a kilometer of solid ice blocked sunlight across the globe? Deep on the ocean floor, hydrothermal vent systems functioned as life's ultimate primordial sanctuaries. Heated by Earth's internal core, these volcanic hot springs were completely independent of surface light and climate. Microorganisms derived energy not from photosynthesis, but from chemosynthesis, feeding on sulfur, iron, and geothermal heat. These ancient chemotrophic ecosystems thrived in total darkness, undisturbed by the planetary freeze miles above. Geological records confirm continuous hydrothermal mineral deposits throughout the Cryogenian, proving these vents never failed. Molecular clock analyses verify vent-dwelling organisms trace their evolutionary branches well before the Snowball Earth era. Meanwhile, specialized cold-adapted microorganisms called psychrophiles established niches directly inside the ice layer. Near the equator, summer melting created thin ice patches, allowing dim sunlight to sustain minimal photosynthesis. Life was squeezed, reduced, and pushed to extreme limits, yet the flame of biological existence was never extinguished. Modern extreme environments show us how life endured, such as Lake Vostok, buried beneath 4 kilometers of Antarctic ice. Isolated from sunlight for millions of years, Lake Vostok harbors thriving microbial ecosystems powered purely by geothermal energy. When the global ice finally receded, oceans flooded with accumulated volcanic minerals, opening endless vacant ecological niches. Free from competitors, the survivors initiated the largest evolutionary leap in complex life history. The Ediacaran period, from 635 million years ago, saw the first complex multicellular organisms emerge. Strange, disc-shaped and frond-like creatures filled the sea floor, representing early experiments in complex body plans. Chemical analyses of Dickinsonia fossils revealed traces of cholesterol, confirming these alien creatures were true animals. Extreme environmental stress acted as a cosmic filter, selecting organisms capable of complex physiological innovations. The survivors of Snowball Earth carried the genetic blueprints that would soon construct the entire animal kingdom. The frozen furnace of the Cryogenian had forged the raw biological material for a world about to explode with life. 540 million years ago, the Cambrian Explosion shattered the biological status quo in a geological instant. Within 20 million years, virtually every major animal body plan existing today appeared in the fossil record. Hard shells, mineralized skeletons, and visual predator-prey arms races transformed the ancient marine ecosystems forever. The Snowball Earth resets provided the raw material, and the Cambrian Explosion was its magnificent expression. Fast forward hundreds of millions of years, as continents drifted and planetary temperatures underwent a long, steady decline. 52 million years ago, The uplift of the Himalayas exposed vast silicate rocks, absorbing atmospheric carbon dioxide. Meanwhile, the isolation of Antarctica formed powerful circumpolar ocean currents, freezing the southern continent into ice. 3 million years ago, the Isthmus of Panama closed, altering global ocean circulation and strengthening the Gulf Stream. Increased moisture delivered to high latitudes fueled massive ice sheet growth across North America and Europe. The stage was set for a new era of rhythmic climate oscillations that would forge the human species. 2.5 million years ago, Earth entered the Pleistocene, a period governed by rhythmic glacial cycles. Serbian geophysicist Milutin Milankovitch solved the mathematical puzzle, explaining how orbital mechanics pace the ice ages. The first cycle is eccentricity, the 100,000-year shift in Earth's orbit from circular to elliptical. The second is obliquity, the 41,000-year wobble of Earth's axial tilt between 22 and 24 degrees. Lower axial tilt produces cooler northern summers, allowing winter snows to survive and build vast ice sheets. The third variation is precession, a 26,000-year rotational wobble that dictates seasonal timing relative to orbit. When northern summer occurs far from the sun, sunlight intensity drops, triggering relentless glacial advances. Deep-sea sediment cores confirmed Milankovitch calculations, revealing ocean temperatures oscillating perfectly with orbital mathematics. Yet, orbital forcing alone is small, requiring powerful planetary amplifiers to create full-scale ice ages. Atmospheric carbon dioxide, ice reflectivity, and ocean circulation currents amplified small orbital wobbles into global freezes. The onset of Pleistocene glacial cycles directly coincided with the emergence of the genus Homo in Africa. According to the variability selection hypothesis, climate instability was the primary engine of human intelligence. African environments fluctuated wildly, alternating between lush lakes and arid savannas every few thousand years. Hominins could not specialize. They had to evolve cognitive flexibility, problem-solving skills, and technological adaptability. Each spike in climate variability correlates with a major milestone in human cognitive and social evolution. 1.8 million years ago, severe climate shifts saw Homo erectus expand across continents. 800,000 years ago, intensified fluctuations triggered the appearance of archaic Homo sapiens and complex tools. 300,000 years ago, extreme environmental chaotic swings forged anatomically modern Homo sapiens. We are literally the children of the ice ages, forged in the crucible of Pleistocene environmental instability. The mental tools that allow us to navigate modern complexity were selected by 2 million years of cold volatility. 26,000 years ago, the last glacial maximum reached its terrifying peak. Sea levels plunged 120 meters lower than today, exposing vast continental shelf landmasses. Australia and New Guinea joined into continent Sahul, while Asia and North America connected via Beringia. Over North America, the Laurentide ice sheet swelled to 3 kilometers thick over modern Great Lakes. Ice pushed south to present-day New York City, depressing the bedrock under millions of tons of weight. Europe lay beneath the massive Fennoscandian sheet, covering Scandinavia, Poland, and the British Isles. South of the ice sheets, vast wind-swept steppe tundra environments spanned across northern Eurasia. This was the Mammoth Steppe, a highly productive cold grassland supporting massive populations of giant mammals. Despite intense cold, this biome supported biomass densities rivaling modern African savannas. Human hunter-gatherer bands survived along these frozen margins, deploying extraordinary engineering and social cooperation. Living in treeless, paraglacial zones, human populations faced severe material scarcity with no timber or clay. In Ukraine and Russia, Ice Age humans created mammoth bone houses, engineering shelters from giant skeletons. At the Milankovitch site, 4 structures utilize bones from nearly 150 mammoths with structural precision. Curved tusks formed arched doorways, while heavy skulls provided immovable foundational support against sub-zero gales. Survival in -40 degrees required advanced textile technology, creating multi-layered, tailored fur garments. Eyed bone needles enabled tight-sewn seams, providing thermal insulation identical to modern Arctic clothing. Weapons technology matched this sophistication, featuring straightened mammoth ivory spears over 2 meters long. Straightening solid tusk ivory required precise heat treatment, patient craftsmanship, and deep material mastery. Hunting massive mammoths demanded complex tactical planning, driving giant game into natural traps and ravines. These humans were not primitive cavemen. They possessed full modern cognitive capacity, adapting brilliantly to environmental hardship. Deep inside dark limestone caves across Europe, Ice Age artists created masterpieces of extraordinary beauty. Chauvet and Lascaux caves contain stunning depictions of lions, rhinos, mammoths, and wild horses, painted 36,000 years ago during deteriorating glacial cold. These artists were true people of the ice. Cave art demonstrates the emergence of symbolic thought, externalizing complex mental models onto physical stone walls. This cognitive capacity for abstract representation is the defining hallmark of modern Homo sapiens. Siberia hunter lineages adapted to extreme cold eventually expanded across Beringia into the unpeopled Americas. They encountered continents filled with naive megafauna, giant sloths, saber-toothed cats, and mastodons. American animals had no evolved fear of two-legged hunters, leaving them completely vulnerable to skilled human tactics. As the last glacial maximum ended, orbital shifts triggered global warming, transforming habitats worldwide. The stage was set for an ecological crisis that would forever alter the planetary megafauna landscape. As post-glacial warming accelerated, the cold, dry mammoth steppe collapsed, replaced by wet, shrubby tundra and forests. Woolly mammoths and rhinos lost their specialized biome, contracting to shrinking northern island refugia. Simultaneously, expanding human hunter populations delivered lethal hunting pressure to vulnerable megafauna. The synergy hypothesis confirms climate stress and human overkill worked together, driving mass extinctions. In the Americas, 35 genera of large mammals vanished within 2,000 years of human arrival. Australia lost 40 megafaunal species, including giant diprotodons, marsupial lions, and flightless birds. On Wrangel Island in the Arctic Ocean, a dwarf mammoth population survived until 4,000 years ago. They outlived the Egyptian pyramids, succumbing only when human hunters finally reached the remote island. Environmental DNA from permafrost confirms human hunting disrupted grazers, accelerating vegetation shifts. The loss of the megafauna closed the Pleistocene, opening the warm, stable Holocene epoch. 12,900 years ago, as the planet warmed, a sudden, catastrophic cold snap struck. Known as the Younger Dryas, North Atlantic ocean currents collapsed, plunging temperatures by 15 degrees in a decade. For 1,200 years, glaciers re-advanced, forcing humans and animals into a final, brutal survival test. Then ocean circulation recovered, triggering the permanent arrival of the warm, stable Holocene epoch. The past 12,000 years of the Holocene represent an unusually stable interglacial climate pause. This extraordinary climate stability made agriculture possible, enabling permanent human settlements and cities. Every written text, technological discovery, and human empire occurred within this brief, warm anomaly. Yet orbital mechanics dictate that this warm interglacial pause was destined to eventually end. Natural Milankovitch cycles predicted the next glacial inception should begin roughly 50,000 years from now. But human industrial activity has introduced a new, unprecedented force into the planetary equation. Atmospheric carbon dioxide has surpassed 420 parts per million, higher than any point in 3 million years. Research published by climate scientists reveals a staggering truth. Human emissions have canceled the next ice age. Accumulated greenhouse warming overrides the orbital cooling forcing, preventing ice sheets from growing. CO2 persists in the atmosphere for tens of thousands of years, altering the planetary climate, pacing permanently. For the first time in 4.5 billion years, a single biological species has overridden orbital mechanics. We have shifted the chemistry of the atmosphere, altered ocean pH, and delayed planetary glacial cycles. We have altered the fundamental engine that created us, pushing Earth into an uncharted, warm state. Species adapted to 2 million years of glacial cycles now face a climate trajectory without historical precedent. While delaying an ice age protects modern agriculture, it trades glacial stability for volatile global warming risks. The experiment is novel, fast, and being driven by an agent capable of understanding its own impact. The geological archive provides the context, but only we can decide how this unprecedented chapter unfolds. Studying Earth's deep history reveals a fundamental truth. Climate does not change in smooth, predictable lines. It is a complex, non-linear system governed by tipping points, feedback loops, and sudden, abrupt reorganizations. A tiny change in orbital tilt or atmospheric gas can trigger a massive planetary feedback response. The Snowball Earth episodes prove that once reflectivity thresholds are crossed, the entire planet can freeze solid. The rapid meltdown demonstrated that greenhouse gas accumulation can vaporize global ice sheets in millennia. The Younger Dryas showed that a single pulse of meltwater can shut down ocean currents and freeze continents in years. When scientists project 2 to 4 degrees of warming, they describe changes equivalent to a glacial transition. These are not abstract numbers, they are geological magnitudes with documented physical precedents. Understanding nonlinear dynamics is critical because human emissions are pushing the climate system toward new thresholds. Respecting the planet's threshold limits is the difference between stability and sudden planetary disruption. Amidst these terrifying planetary convulsions, one overwhelming lesson shines through: the incredible resilience of life. Life survived a frozen ocean covering the entire globe, enduring conditions that should have been universally fatal. It persisted in pitch-black hydrothermal vents, in subglacial lakes, and in thin equatorial melt pools. And every time the planet thawed, life did not merely recover, it exploded into unprecedented complexity. The Cryogenian freeze birthed the Ediacaran multicellular forms, and the post-glacial world enabled the Cambrian Explosion. The environmental crucible of the Pleistocene forged the problem-solving intelligence of our own species. The biosphere has survived 5 mass extinctions, global glaciations, supervolcanoes, and asteroid impacts. Nature will endure whatever the current climate experiment produces, long after human civilization responds. Life is an unstoppable cosmic force, converting extreme stress into evolutionary innovation over eons. The story of Earth's ice ages is ultimately not a tale of death, but of biological triumph. For 4.5 billion years, planetary climate was driven by geology, solar physics, and orbital mechanics. Today, for the first time, a biological species has become the dominant driver of global climate change. This new geological epoch is called the Anthropocene, the era where human activity reshapes the Earth. With this unprecedented power comes a profound, terrifying evolutionary responsibility. The brains forged by 2 million years of Ice Age instability must now be used to preserve planetary stability. We are not separate from nature. We are its living, conscious remnants, carrying its ancient legacy forward. Understanding the deep geological past provides the vital map needed to navigate our climate future. The choices made in this century will echo through the geological record for tens of thousands of years. Humanity stands at the ultimate crossroads between stewardship of a living planet or catastrophic disruption. Look around at the modern landscape. Every valley, lake, and fertile soil carries the mark of ice. The Great Lakes were carved by the Laurentide ice sheet, scouring deep basins into solid bedrock. The rich agricultural soils of the American Midwest and Europe are glacial loess wind-blown sediments. Our modern food production systems rely directly on the fertile legacy left behind by retreated glaciers. The Hudson River Canyon, Norwegian fjords, and Irish drumlins are physical monuments to glacial dynamics. Beneath our feet, the Earth's crust is still slowly rising in a process called isostatic rebound. Scandinavia and northern Canada rise millimeter by millimeter, adjusting to the loss of heavy ice sheets. The physical record of the ice ages is written into every rock strata, cliff face, and ocean sediment core. The planet remembers every freeze, every thaw, and every cosmic collision that reshaped its surface. We live upon the scars of an ice planet, enjoying a brief, beautiful moment of planetary warmth. A boiling molten furnace, a frozen snowball world, and 2 million years of rhythmic glacial volatility. The history of Earth reveals that our comfortable world was forged inside cosmic trials of extreme cold. The Ice Ages created the landscape, sculpted the biosphere, and selected for the human mind. Now, as we alter the atmospheric chemistry, we hold the steering wheel of planetary climate history. Which of these terrifying frozen transformations do you believe poses the most profound question to our future? Share your fascinating theories and insights in the comments section below and join the deep discussion. Be sure to subscribe to Remnants of Time right now for more deep dive classified historical documentaries. Click the notification bell to join our global circle of investigators before the algorithms bury these truths forever. Thank you for watching. Stay vigilant, keep questioning, and we will see you in the next deep void. Remember that the ground beneath your feet is always keeping score. Sleep well, knowing the past is watching.